Hi friends, in the continuation of data science interview question answer series, we are moving to question difference between data warehouse versus operational database. Primary goal, online analytical processing, OLAP, supporting business intelligence reporting and complex analysis. Online transactional processing, uh, supporting day-to-day business operation and fast transaction data structure, data warehouse normalized schema example star snowflake optimized for read performance and aggregation, operational dataset normalized schema optimized for write performance and data integrity acid rules, data time frame data warehouse, historically a time variant data often aggregated over years. OLTP is based on the current and up-to-date minute data stores only the latest state of the business data access. Data warehouse few complex read queries that access many records, full table scan. Operational data basis many simple read-write queries that access a small number of records, single row lookup, read-write ratio, data warehouse, read heavy, write once, read many, operational data bases, write heavy, frequent insert, update, delete, consistency, data warehouse focuses on eventual consistency during data loading via ETL or ELT. Operational databases require strong consistency acid rule to ensure every transaction is accurate. Level of details. Data warehouse often store aggregated, summarized data through atomic detail can exist. Operational data set store highly granular atomic data. Example, every individual mouse click or transaction. Example, data warehouse analyze sales trend over the last 5 years by region. Operational data base processing a single customer order checkout in real time. Moving to difference between precision and specificity, true negative rate formula, true positive divided by true positive plus false positive. Uh, in true negative rate, true negative divided by true negative plus false positive. Questions: of all we said were positive, how many were actually positive? In specificity, of all the true negative cases, how many did we correctly identified as negative? Focus. Precision measures the model quality when it predicts positive, minimizing false positive. Specificity measures the model quality when the true class is negative, minimizing false positive interpretation. Precision, high precision means when the model fires an alarm, it likely to be right. Specificity, high specificity means the model is excellent at rejecting negative, minimizing alarm. Error type focus. Precision, minimize false positive, type 1 error. Specificity also focus on minimizing false positive but relatively to actual negative. Use case example. Precision, a search engine result. High precision means most of the few top results are highly relevant. Specificity, a lie detector test. High specificity means it rarely flag an honest person as a liar. Use case 2 example, spam filter. You want to avoid flagging an important email as spam false positive. Medical trials, ensuring a healthy patient is correctly identified as healthy. Model trade-off, precision often trade-off with recall sensitivity. Specificity is complete of complement of the false positive rate FPR equal to 1 minus specificity. Moving question, difference between hard clustering and soft clustering. Assignment type. Hard clustering, exclusive assignment, each data point belongs to exactly one cluster. Soft clustering, probabilistic assignment, each data point has a degree of membership in every cluster. Output, hard clustering, a single cluster, example 1, 2, 3 for each data point. Soft clustering, a vector of probability or scores for each data point corresponding to each cluster. It's point 8.1.1.2 data points on the boundaries. Hard clustering boundaries points are focused into the one cluster, potentially leading to incorrect or unstable assignment. Soft clustering boundary points are assigned partial membership to multiple clusters, reflecting uncertainty. Model type, hard clustering, centroid based or density based, example K-means, DB scan. Soft clustering model based, example Gaussian mixture model or membership based fuzzy C-scan. Interpretability, hard clustering simpler to interpret and apply. Result are straightforward customer segmentation. Soft clustering, more complex to interpret, require analyzing membership weight to understand blending. Loss function, typically based on the squared error distance to centroid. Soft clustering, typically based on maximum likelihood estimation, assuming underlying distribution. Use case, hard clustering, physical grouping, market segmentation where distinct groups are desired. Soft clustering, image segmentation, cluster behavior analysis where blending segments is likely. Flexibility, hard clustering less flexible, cannot naturally handle data point that granularly belongs to two groups. Soft clustering more flexible and realistic for data where boundaries are naturally blurred. Moving to question, feature importance versus feature weight. Calculation method. Feature importance measures the changes in the model performance, example MSE or accuracy when feature values are randomly shuffled. Prematured feature weight, the learner coefficient associated to each feature during model training. Model type, model agnostic but often used complex non-linear model, random forest XGBoost neural network. Feature weight only applicable in linear model, linear regression, logistic regression, linear SVM. Interpretation, feature importance, marginalize impact, how much the model relies on this feature for overall predictive power. Feature weight, directional impact, the direction and magnitude of change in the output for unit change in the feature. Scale dependency, feature importance generally independent of the feature scale if done properly on the normalized dataset. Feature weight, high dependent on the feature scale. Larger weights can mean a smaller scale feature is important. Handling collinearity, feature importance can misleading if two features are highly correlated. The importance can be split between them. Feature weight can be unstable and highly varied. Example, large positive weight on one and large negative on the other if not regularized. Result unit, feature importance expressed in the unit of the model loss. Example, 10% increase in MSC when shuffled. Feature weights expressed in the unit of the target values, example plus $500 in the price per unit increase in size. Global and local, feature importance provide a global measure of the features importance across the entire dataset. Feature weight provides a global measure of the feature importance impact its slope across the data space. Tool libraries, feature importance often implemented via sharp line or library specify method, example Guinea importance directly accessible from model coefficient or model parameter attribute. Please like, subscribe and share the channel. Thank you.